So this chapter will look at so called 2k factorial designs. So there are k factors and exactly 2 levels per factor. Right. So full factorial is simply 2 to the power k, right. So if I really want to vary all combinations, I have 2 to the power k combinations. Okay. So now this is so designing experiment is simple, right. Now we will take a special case first. So let k is 2, very simple. So I have only 2 factors, and in this case let us say memory, main memory size and cache size, and I am measuring the performance of a CPU in terms of MIPS, and your goal is to find out which has more impact, memory by itself or memory, or what is the proportion that memory has on the performance of the overall system, or cache size has, or a combination of these two. Okay. So here is your table, right. So we look at this numbers first, and then we look at some derivations later on. So performance of a system measured in MIPS. There are 2 levels of cache size, 2 levels of main memory size. So this is cache, this is main memory, this is 4, this is 16. Okay. So this is measured from a set of experiments, and notice there is no replication, it is simply 2 to the power k. So I have 4 combinations for these 2 factors, and just one value from one experiment conducted for them. Chapter 18 will talk about 2k to the into r, that is separate. For now just look at one value, one experiment conducted for each of these parametric 4 factor combinations. Okay. This is 25. Questions? Okay. So let us use a couple of indicator variables. Yes, if you look at chapters 14, 15, which talk about multiple linear regression and so on, there given the values of these xy, right, or the factor combinations, you can try to predict what the value for your y, which is your performance in MIPS, can be. Here we are not exactly doing that, we are doing something slightly different. So these are your indicator variables. So let y denote the response variable. In this case it is oops. So what I want to do is I want to express y, this nonlinear regression, this format. So qa is a quotient, xa remember is your variable, qb is a quotient to be determined, xb is the variable, then there is the combined impact, right. This is called the interaction factor. So given values of xa and xb, right, I try to find out this value for y, and why do we do this we will get to know later. Okay. So even though, so whether this is 4 or this 8 does not matter, it is still coming to -1, this could be 24 or 32, it does not really show up in your indicator variables, right. In this case it is simply ignored, even though that will make a big difference to your performance, but if you change to 32 then correspondingly y also would have changed, right. Okay. Alright. So now our job is to find out these coefficients and then we will see how we can use that, right. So how do we find the coefficients? This q naught, qa, qb, qab. No, you just have to write this equations, right. You do not have to go there, it is simply a set of linear equations, right. So what is y? 15, right. So 15 is q naught plus qa into 1 or -1 rather, right. So we can simply write the set of linear equations, okay. So 15 is given by q naught minus qa minus qb plus qab. So why is this minus? Because of the fact that xa is -1, right. For this value xa was -1, xb was -1 and xa into xb is 1, so that is why you have this one, and then you have next 45 . So this is directly from the table as such, right. Only thing that I am inputting on this side is this y value which is measured, right. Everything else is simply that -1 plus 1.
Perfect fit.
That is assumption that we are making.
No, because then this might not have a solution, right.
Oh,
if there is no perfect fit, it won't have a solution.
There is no perfect fit for this particular set. Will this be a case where your solution does not exist?
Solution will occur only if there is a perfect fit through these points.
We are not actually trying to fit your y to the values of x and, right. xa and xb are only plus and minus 1, right. And if you are thinking of fitting the value of y to the actual values of 4 MB and 16 MB, is that what you are trying to do, or right? Yeah, that's we are not doing that. We are not trying to do that. We are only trying to find out what is the impact of the first factor over the second factor. What is the relative impact of these factors? We are not trying to do a prediction, right, based on the linear or other regression. This is only trying to find out relative impact of these factors. Okay, so when we compute the y's, the qa's, then we will see why this is making sense. Right. I am not trying to fit the data to the exact values of on the x-axis.
Not -1.
Then all many of these will go to 0.
Yeah, it becomes a sparser matrix and easier to compute, right?
Okay, but will we still get our qa's? Will you be able to get our qa and qb? See, if this is 0, it will be 0, so it will be simply y equals q naught, right, and this whole thing will go to 0 in the first case.
You will already get q naught choosing 1. The next thing.
But here the q naught is what we find actually will be the mean of these 4 values. Yeah, I didn't think through why they didn't use 0 1 1, but it didn't seem to make sense here. You will get y equals q naught, right, or y1 equals q naught, then y2 will be qb, right, but that does not help explain the variation. I haven't done that much digging in to see why that 0 1 would not work.
Yeah, we are fitting.
We are still trying to fit.
Yeah.
You are trying to fit and predict, okay, but you are only fitting with the
That's
predictor
not
variables.
right.
Y is the
this,
yes,
set
you are
of
fitting
input
this to the predictor variable, to the indicator variables than the actual values of the variables itself, right. You are only the indicator variable is
given a configuration. What is the corresponding y is what we are trying to do.
no. We are yeah. What we are trying to do is we are finding these QAs and then using the QAs to figure out whether your main memory has more impact on the system compared to the other system. That is what actually we are heading to. Yes, yeah.
Get the QAs, that is the assumption you are making.
Okay, so in this case you are saying that
y can be fit through this.
so that what if there is no fit for this particular set of values, right? I don't see why there will be no fit the way that we are doing the computation.
XA XB factor.
XA and XB is 1 into 1, right? So here XA and XB, your XAs have all become minus and plus or minus 1, right? And also you want to find out whether the 2 factors combined have more of an impact or not. If that QAB is very high, the proportion of variation that this QAB gives, which I will talk about later, is very high, that means that the 2 factors combined have more of an impact than the system, okay. So if you notice, right, in this all these 3 columns, the all adds up to 0. If you look at yeah, right, column wise except the first column, everything adds up to 0. So we can now solve this, right, and I won't spend too much time trying to figure it out, but this is basically what you will get. Okay, so these coefficients, so what, right, these coefficients are called your effects, right. So the coefficients so what we say is the effect of your first main memory is 20 and this one is 10, this one is 5. So there is a relative, right, grading between these two in terms of how much impact they have on your system as such, right. So effect of okay. So in general for this if I am giving you be the response variable values, yeah, this is y. So y1, y2, y3, y4, right, be the response variable values. So rather than solve this equation every time, those set of right, linear equations, we have a shortcut table method that lets us figure this out. So we have the, so let us write it this way. So there is a column A, column I, A, B, and this is your column Y. These are your 4 set of experiments, right. So I is your identity column, so or vector, whatever it is. So this is all 1 and this is, right, minus 1 minus 1. Remember for minus 1 represented 4 MB main memory, minus 1 here represents your cache of 1 KB, right. So what is the value here? 15, and this was 45, this was 25, this is 75. Okay, then this was changed. Slightly different from how we write our zeros and ones in binary, right. There we always vary the LSB first and then do the MSB last. Here you can still do that way too, but we will stick to the book's way. So your MSB varies first and then your LSB varies next, right. So these are the 4 combinations of A and B values, XA and XB. So what is A into B? A into B is simply the XA into XB, right. So this is 1 minus 1 minus 1 1. Okay. So this is our same table that was given to us in this particular form. So what we do is for each of these columns do a column wise, what is this called, dot product of this column with y, next column with y and so on. So what do you get? So this is simply the summation of all those fellows, right. So this is 160, this is 80, this is 40, okay. So this is here, right. Then divide this whole thing by 4 or 2 squared, the number of experiments, number of rows in your. So what is this? 40, and that's, these are your coefficients now. So that is a faster way to compute these values, and that is why also where minus 1 plus 1 is useful. If I do 0 1, I do not know what will happen, you can try that. Okay, so still we have not got to the point what is the big, what do we do with these fellows, right, with these QAs. So is this, so given a set of 4 experiments, 2 squared experiments, and given the corresponding y values, I can compute the average. So Q naught represents the mean of those 4 experiments. Sometimes it makes no sense to actually compute the mean because okay, mean MIPS of all these 4 experiments is this, but I am more interested in what is the impact of the other variables of these factors on the system performance, right. So from what we can see, QA is higher, right. But if you really want a quantification of the proportion of the importance of a particular factor, then this is what we do. Okay. So we now do we are going to look at so called allocation of variation. Okay. So what is that defined as? So your sample variance, right. So y has 4 values, right. So your is nothing but so this is your definition of sample variance, right. So in this the numerator is called your SST, which is basically sum of squares total. So it is simply the square, right, sum of the difference of each value yi with respect to the mean of those 4 values. We can now prove, depending on how much energy you have, SST equals so the total variation, right. So this is your total variation. So this is let me add this, right. This is called your not variance, this is called variation, right. Variance is your SI squared, this is simply called variation. And so this is out of the total variation in the performance, the amount of variation that is contributed by your first factor is this one, right. So this is the variation due to factor A. And this is due to factor B, and this is due to interaction. And we call each of these as SSA, SSB and SSAB, sum of squares with respect to A, with respect to B, and with respect to the interaction between these two factors. So we generally write that as SST equals okay, and the fraction or proportion of variation explained by A So finally this is what we are coming to with our QAs. Once you determine the QAs, then I compute the fraction of variation for each of the factors and the corresponding interactions. Okay. So that is the theory. So let us look at our example, right. So in the previous example, what is SST? Our mean was 40, right, Q naught was 40. So it is 40 minus 15, so that is 25 squared plus 15, then it was 45, 25 and 75, right. So I can compute SST in two ways. I can directly compute from the actual values of y, or I can also compute SSA, right, SSA plus SSB and so on, and which is also equal to how will this proof? You want the proof of that? Yes. Yes.
I mean,
Next.
what have you substituted for what? The uniform.
Sigma form. Using the sigma form you have computed.
Using this one, we will be able to derive that. So this is the definition. Two into two, yeah, that is the number of experiments that we have. Yeah, this is since if it is k factors, it will be 2 to the power k.
Okay.
And the other thing will be squared still, but this will be 2 power k into qa squared plus and so on, qb squared, qc squared, qd squared plus all the combinations of a, b, c, abd and so on.
The formula which you had implicitly done.
last one.
Yeah.
Should be divided by 2 square minus 1. 25 square plus 5 square plus 15 square.
No,
plus
no, I am only taking the numerator.
SST.
I am not. I am looking at the variation. Numerator is I am not looking at the variance at all. This is only the variation. That is the definition. Statistical. This is variation. So that's why you are not dividing. Okay. So this is 4 into 20 squared, 4 into 10 squared, 4 into 5 squared, which by magic is, this is also 2100. So I am just explaining the rationale. We will come to the proof very soon. See a lot of demand for that. Okay. So what is SSA now? SSA is 4 into 400 1600, SSB is 400, SSAB is 100. So therefore, what I finally want to come to is the SSA fraction, right. So the fraction of variation that is attributable to factor A is 1600 by 2100, which is 76%. Okay. So this is what we are trying to get at to find out. So with this we can say that factor A is more important than factor B, and the interaction between these two factors is small. I am not trying to predict the value of y, I am just trying to find out which has more impact. So if you want to convince your administration or your boss saying that we have to invest more money in main memory, this is your way to do that, right. If you just present the table, with the table you may not be able to get a more concrete picture, saying that yes, it looks like, because in 15 to 45 if I increase memory, 25 to 75 there is some increase, right. But if you want to have a more quantified way, assuming that big bosses understand these things, right, you would use this as your way to demonstrate, saying that this is the way that I can explain the variation. So the contribution of each of these factors to the total variation of the system is basically computed as follows. That's all.
Say I want to recommend a server for my client. Example, this is day in day out what we also do, where we have a say n number of network elements, and we have a constant data generation because we keep on pooling these devices for the data. And what type of a server should I recommend, with what memory, what is the, say I have say thousands threads running for pooling these the equipments, and there are 1000 devices and they generate say 5 KB of packet at every 5 minutes.
Okay.
So in such cases, how do you suggest this kind of analysis is useful?
So in this case you have to do some sort of basic performance measurements, right, varying your memory, your CPU speed, the number of cores on your CPU, right, that you are having, and the different CPU types also if you want, right, between Intel and AMD and so on. So that is, these are your levels, right. CPU type itself is one, main memory also is another level, right. So main memory.
Typically I have one question. See, IBM guy comes and tells me all his specifications, HP guy comes in with his specification of the server, and this one guy comes and gives me this.
Okay. So you basically only know the CPU type, right, and then okay, so that you have only one variation, right. So you have different types of servers, and they are giving you different MIPS numbers for all of those, and then you want to see which one is going to be better, okay, right. So how do you make the decision? When you have, if you simply go by MIPS, right, you have to look, if you have, it depends on what your cost benefit ratio is and whether you trust their MIPS or not, right. One is you have to test it in your own setting to find out whether for your experiment these right, these factors are making all these different systems give you different performance measures, right. And then in your test, if you simply say this gives me the better performance measure, then again you have to go back to our comparing alternatives that we saw, right. You will conduct enough experiments, enough workloads, enough variations, and then you can say that with replications I am actually able to show that one is better than the other conclusively, right. If one system is persistently better because they have very good internal architecture for the CPU and the way they utilize memory and cache and so on, then you would do that, right. So here in this case you are trying to analyze the different factors that you would like to see, right. If you want to improve something, if you want to I guess redesign the system, right, or add capacity to the system, the question is where does it make more sense to add, is it main memory or is it cache. In this case what these results show is that main memory is giving you much more performance benefits than this cache, but the tricky part here is your cache values are very small, right, from 1 KB to 2 KB, that is only a doubling of cache capacity, whereas memory I went from 4 to 16 MB. What if I had gone from 1 KB to say 8 KB cache, the same set of experiments, your coefficients will be different. In that case you might say that, right, the two of them might end up giving you same performance improvements, right. So that is, we will have to look at several variations of this to figure out which of these is finally, right, giving you. This is again just depends really upon the values you have set for those parameters, the two levels that you have chosen, right. So it is not like one set of studies with this and I am done, right, you will have to look at other variations also. So that is why again you are only looking at two levels, you should be really looking at L levels and then K, so it will be L power K factorial design is what you really like to do, right, L dimensional, but this is simplified in that particular sense, because many times you are down to two alternatives, just one of these two is what you want to decide. If you go management saying that there are 10 alternatives on this and 10 alternatives on that, let us choose one, it is going to be tough to convince. You say these are the 2 and 2 and then you can simply pick one, so you have to do this filtering and then come down to these two at the end.